So thank you. So today I'll be talking a bit, as Jeff just said, about small impact crater populations on the moon. And by small, I'm talking about 600 meters to 10 kilometers. So the goal of this project was to investigate lunar impactor size frequency distributions through time and improve estimates of the impact rate since the LHB. So we're primarily concerned with the time frame along here. And we had several motivations for this project, and that previous work, especially on the impact rates through time, needs updating. Most of it is at least 20 years old. There was also little work for this particular age range between about 1 billion years and 4 billion years ago, and also for this diameter range. And that's where the outstanding LROC imaging comes into play. The WAC global mosaic is at the perfect resolution to study this diameter range. And then there have also been recent development in numerical approaches improving chronologies and our understanding of the evolution of impactor populations. So our approach was to compile and analyze small superposed crater distributions on the floor of several larger lunar craters. And by large lunar craters in this case, we're looking at primarily those with diameters between 80 and 100 kilometers. And this is our selection of 40 craters on the lunar surface that we examined their crater floors. And these craters were selected from a larger distribution, about 150 named craters of this size, based upon mostly imaging availability. The WAC mosaic is very nice, but there still are portions of it that aren't the best for examining crater distributions. And we also had to consider secondary populations. We didn't want to examine craters with lots of secondaries on top of them. So, but it still remained a wide distribution in latitude and longitude, and actually also age. Although we did not examine craters younger than about 1 billion years, like Tycho and Copernicus, because they just don't have enough of these 1 kilometer craters on them for the statistics we need. So a brief discussion of our methods. First, the small superposed craters were measured in JMARS and assigned a degradation class of 1 through 4, where 1 is fresh and 4 is most degraded. And we also assigned if they were an obvious secondary crater, and by that we just mean if they formed in a cluster or in a chain. Once we had the small superposed craters compiled, we computed the model age of the crater floors using the Markey et al. Model production function. And the important thing to know about this production function is that it is based upon observations and models of impactor populations, and in our case we're using the NEO population. And then the impactor population production function is converted to a crater production function using scaling laws. And for this work we're primarily using the Melosh gravity regime scaling law. So once we've computed the age, which is just a basic fit of the model shown in white here to our data points shown in green and a cumulative plot by reducing chi-squared, and so then we get an age for the crater floor. And once we have the age, we have assigned a Stoffler epoch from the 2006 paper, and we've assumed the 3.85 year age for Nectarian, for Nectaris in this case. And this is to facilitate comparisons to past USGS identifications on the global lunar maps that were produced in the 60s and 70s. As for most of our craters, actual absolute ages were never computed, just the epoch was estimated. And we can also compare by doing this, we compare the shape of our crater SFDs to the MPF. And that's our first result, in that we find that almost all of our SFDs were consistent with the MPF. And here I show 3 examples at 3 different ages, showing that they cover a wide range of age and crater density. And this is an indication that the MPF is possibly a very good representation of the impactor population, in this case the NEO population, and that our data is hopefully mostly primary craters and not very much contaminated by secondary craters. So once the ages were computed, we decided to plot them up in this format where we look at the actual individual. The ages are plotted as Gaussians, which also indicate the error on the ages. And here, the individual age Gaussians are shown in the dotted lines, and the numbers here just mean that there are overlap of some of the data, and that's telling you how many are there. But the more interesting feature is looking at the sum of these Gaussians, and two very important features pop out, and one is that the LHB may have an extended tail even to ages younger than 3 billion years ago, and that there has been little cratering since about 2 billion years ago. This is really just representing one possible crater that has occurred at this time. And I should mention that this is looking at a subset of our data, that these are just original crater floors. So these craters have not likely been resurfaced, so we're actually looking at the formation age of these craters. This is just another way to look at this idea that maybe there has been little recent cratering of these large 80 to 100 kilometer craters. And so what we have here is showing the Stoffler epoch for our ages, comparing to the previous determinations from the USGS maps. So, and we find that for 50% of our crater floors, which are all shown here, our ages are older than the previous determination. And this includes actually all former Copernican and Eratosthenian crater floors of this size crater. So one possibility is, of course, that there's issues with our data and calculations, and that, of course, even most recently, these boundaries are still not definitively defined. There's still debate upon where these boundaries fall age-wise. And then, of course, chronologies are still being refined, so our data may have some small error as well from that. But the more interesting thing is that there are actually issues with the original USGS interpretations, which were based upon lunar orbiter images, which were not as nice, especially on the far side, and that they were also sometimes using what was called a DL, a degradation statistic, which has since been shown to not be robust in determining relative crater ages. So, and what this might mean is that the crater floors, or the craters themselves, are actually older than originally predicted, and there may not be as much young cratering earlier or crater younger than 2 billion years. We do have a few that are not consistent with the MPF, and so we did not compute ages for these craters. They are randomly located across the surface. They also have a wide range of crater density, or crater cumulative densities at 1 kilometer. But this the smallest cumulative density for Rosenberger is equivalent to one of our craters that is consistent with ages about 3.8 billion years. So these are still very old craters. And this may give us a clue to why they may not match. Now there's 3 different things we can look at, and 2 of them have to do with the MPF itself, the production function. And one is, should we be using a different population, impactor population? The one we have been using is represented here by the NEO population. But this one here, which represents the MBA population, maybe that's more appropriate. It's a little bit shallower here. However, the data for the actual main belt asteroids only goes down to about 0.5 or 500 meters diameter for the impactors, which is about equivalent to a 10-kilometer crater. So, sorry. This part here is just data from the actual cratering on the lunar highlands. So, so we don't actually know where in the size range we're looking at for the superposed craters if that trend continues or if it does something different. So the scaling law is also a possibility. So we have been using the Meloche gravity regime, but strength regime may be important for smaller craters. And this is showing an example that's incorporating actually a layered strength regime, so 2 layers with different strengths. And we find that the Rosenberger data is fit better by this particular scaling law, but we don't know yet if this is an appropriate change to the MPF, as we don't have observational data for layering. But finally, the most simple explanation is that SFD itself has been geologically modified by resurfacing. So here we have a crater, Mintzev, that has a distribution that's not consistent, compared to the geology of a crater that has a distribution that is consistent. And you can see the obvious changes in the geology between those 2 craters. Also, if you look at the individual degradation classes for each of the craters, the superposed craters, you find that they're mostly degraded class 3 and class 4 craters. So final slide is that on a different note, we can also look at the distribution of the obvious secondaries that we've been measuring as well, which have not been included in the data set so far because we didn't want them to influence our primary crater data set. But we find that if we look at the differential slopes, we find that there's a wide variation from very shallow to very steep slopes for the secondaries, which is not the same as what we've understood for average secondary distribution. And this may be related to formation of individual secondary crater fields, which we don't understand very well yet. So conclusions are that we do find agreement between most of our SFDs and the MPF, the model production function, and this further validates that production function, and that our crater distributions are largely characterized by primary craters. Model ages may indicate that our craters, that the LHB had an extended tail. Ages are older than initially ascertained, and this may be due to less cratering during the Copernican and early Ratostinian than originally thought. And few of our distributions are not consistent with the production function, and this is likely due to geological activity. But MPF inputs can be adjusted to improve the fits, but we don't know yet if this is appropriate. And obvious secondary fields, SFDs, have a wide varying slope that are likely representative of different type of secondary cratering. Thank you.
Okay, we have time for a question. Dr. Morrison.
That's very interesting. I'm wondering, instead, if your results hold up on the ages of the craters, wouldn't it be more consistent, instead of shifting them from a particular crater from, say, Copernican to Ratostinian, to just change the age dates corresponding to those old USGS categories?
Well, yeah. So basically, the idea is that, of course, you could consider that the boundaries themselves need to be shifted, but the main idea is that our ages are older than you might have associated with these craters in the past. So, yeah, but there's, of course, several factors coming into play in those comparisons.
So I'm going to ask one last quick question. Is Copernicus still a Copernican crater?
Yes, it is.
All right, and on that note.
Next speaker is